let's move on to talk about another very important measure of dispersion, and that is standard deviation. And standard deviation is a very important measure. Standard deviation is a measure of how spread out observations are. So if you look at the diagram on the right, as we've already talked about, you see different degrees of spread for the blue, the red, and the green distribution of data. So with these three distributions here, we have different standard deviations. But again, note that we have the same mean. So again, if we've given this job satisfaction survey to three groups, maybe divisions in our business, they come back with the same mean, but again, different standard deviations. So as I've said multiple times, and I'm sure I'll say it again before this lecture is over, so please forgive me, but it's an important point. Simply reporting mean satisfaction is not really sufficient for painting a full picture of your data. If you go to the trouble of collecting the data, why suppress data by not giving people as much information as possible? And the mean only tells part of the story. Now, when we're calculating standard deviation, notice that we have two different equations depending on if we're talking about the population or the sample. And by now you understand what we mean by population and you understand what we mean by sample. Note that we have two different symbols, right? We're using sigma in the top one for population standard deviation, but we're using S when we think about the sample standard deviation. So that's one big difference. We just have different notation when we talk about population and sample. But on top of that, we need to remember that we have different means. In the top equation, we've got mu. And mu, if you recall from previous lectures, is the population mean. But in the bottom equation, we've got x bar, where x bar is the sample mean. But they're basically doing the same thing. Do you agree? They're looking at the sum of xi minus mu, or xi minus x bar. We're taking each observation, subtracting the mean, and then squaring it to get rid of any negative sign. Now, the next thing that we see here is that when we look at division, what's on the denominator of this, we have n for population, but we have n minus 1 when we're calculating the standard deviation for the sample. So we're not going to get the same calculation, right? Again, one is looking at deviations from the population mean, the other's looking at deviations from the sample mean. One is dividing by n and the other is dividing by n minus 1. Now, hopefully you're thinking, why? Why is that? Why is the population divided by n whereas the sample is divided by n minus 1? Well, the answer is it reflects what we call degrees of freedom. And we're going to talk more about degrees of freedom. But basically, the sample standard deviation calculation loses a degree of freedom. And the reason it loses a degree of freedom is because we are making an estimation. We're making a guess. And what is it that we're guessing about in the equation? Well, we're guessing about the population mean. We're estimating it, right, with x bar. So x bar, our sample mean, is our best guess for estimating the population mean. And because we're estimating something, that costs us a degree of freedom. Now, I'm going to ask you to review this idea of degrees of freedom in the resources in the module, either after this lecture or in another location. But do understand, we're going to come back to this idea of degrees of freedom more than once. It will be an important concept, especially when we get to the idea of regression analysis. But the takeaways here, let's be clear, we have two equations, one for population, one for sample. We use different symbols. We use different estimations, right, of our mean. We've got our population mean mu. Up top, we've got our estimate of the population mean, x bar, our sample mean. But in both cases, we are looking at observation xi, subtracting the mean. So how far does that observation deviate from the mean? And then we're squaring everything. In the top equation, we're dividing by n. The bottom equation, we're dividing by n minus 1, reflecting different degrees of freedom where we lose one for our calculation of sample standard deviation. Now, as I've already explained multiple times, we see what's going on in that parenthesis, but let's look at it just one more time. So let's take for our sample. So we have a sample, let's say 10 observations, and xi is one observation. So we could be looking at x1, x2, x3. And for each one of those observations, I'm subtracting off the sample mean x bar. And so I'm basically capturing how far is this observation from the mean. And do you agree with me that sometimes it's going to be a positive number and sometimes it could be a negative number, right? If I'm looking at an observation of 5 minus 4, it's positive. But what if it's 5 minus 7? Then it's negative. So, see that squared term? That squared term is there because it's basically going to eliminate the negative sign. Because, as these bullets say, some observations in my sample are below the mean. They'll be negative in that bracket. Some observations are above the mean. So the term in that bracket is going to be positive. But here's the problem. If I have some that are positive and some that are negative, they could just cancel out, and then I have no deviation. So if we square them, as we see here, we've got that parentheses expression squared, then everything is expressed in the positive. Now that might not quite make sense yet, but just give me a second and I think this will help. So let's say that I have deviations. I'm looking at that bracket, right? What was in that bracket? And let's say I have +4 and +4, but then I have some observations below the mean, so I have -4 and -4. So +4, +4, those are observations above the mean. -4, -4, those are observations below the mean. So if I just add them all together, like in that summation sign, I have 4 + 4 - 4 - 4 divided by n, which is 4. So here's the problem. I'm going to end up with 0. So if we don't square the terms, my positive terms cancel with my negative terms, and then we ended up in this example with 0 in the numerator. Well, what would it mean to have a 0 in the numerator of my standard deviation calculation? Well, I'm going to end up with standard deviation being 0. So what we'd be saying is that we have a distribution with 0 spread. But is that the case? No, because we have spread, right? We had 2 observations that were above the mean, and we have 2 observations below the mean. Clearly, we don't have a 0 spread. But without squaring those terms, everything cancels out, and it makes it look like I don't have spread. So squaring that term in the parentheses, that keeps things from canceling out. So, when they're squared, let's think about what happens when we square the same terms right here. Well, 4 becomes 16, 4 becomes 16, but now -4 becomes 16, and -4 becomes 16. Now I have 64, and 64 divided by 4 is no longer 0. So hopefully that makes sense. This is not atypical in equations where we square terms to eliminate the idea that some things are above and some things are below, and we don't want them to just cancel out. You'll see that again. So standard deviation can be hard to intuitively understand, and it's a little bit of a messy equation, and it's a little abstract, but it's such an important idea. It offers us a standard way of thinking about spread, right? How can I know if something is a big spread or a small spread without some standard measure? So this is a standard measure that then helps me describe spread in a way that makes sense and I can compare. So I have found this amazing dog example to illustrate. I'm going to be honest, this is not mine. I do document where I came upon it, but I've not seen anything better. So let's take a look at this. Let's say that we have a sample of dog heights, and these are reported in millimeters. So I don't know, maybe this is a European example. Clearly we wouldn't be reporting in millimeters here in the United States, but we have samples of dog heights in millimeters. And first we need to find the mean. And I need the mean so I can measure how far each observation is from the mean, right? Some are going to be above the mean and some are going to be below the mean and some might be at the mean. So if I take this data and I calculate the mean, it gives me 394 millimeters. So the mean height for dogs in this sample right here, 394 millimeters. So how did I do that? Just like this. I took 600 plus 470 plus 170 plus 430 plus 300 and divided by 5 dogs, and that's where I got 394. But you probably already caught on to that. Now, I've plotted my mean there in green. And just as I said, we're going to have some dogs below the mean, some dogs above the mean, and some dogs that might be close to the mean. So I've got my mean in green. And now I can look at the distance from the mean for each dog. So do you see in the bottom picture, I've got my green line for mean, and then I'm measuring deviation from the means. For example, that first dog is 206 millimeters over the mean, but the last dog is 94 millimeters below the mean. So some are positive, some are negative when we calculate deviations from the mean. And now remember what we talked about a minute ago. Do I just want to add these all together? No, because they're going to cancel out. That's not what we want. So we need to square them. Just like in that equation for standard deviation that we thought about with that squared term, that's exactly what we're doing here. We need to take the square. When we take the square, it's going to express all of these deviations as if they're positive, even though they're not all positive, but that's going to keep them from canceling out. All right. Then I need to take the sum. So remember, the equation for standard deviation is we want to look at xi minus x bar and square each one. So xi is each dog, x bar is my sample mean in green, and I want to look at the deviation for each, 206, 94, and that's what's in that parentheses, and I square them and take the sum. All right. So when I do that, when I square each one, and that makes it positive, and then I take the sum, I end up with 108,520 millimeters. All right, so back to our equation. So our sample standard deviation, look at the part that I've got in red. As we just said, we want to take the sum of the deviations from the mean of the sample, that's x bar. So I need to do that for each of the 5 dogs. Some were positive, some were negative, but we squared each one so that they don't cancel each other out. And when I add those all together, I get 108,520 millimeters. So that's what we just did. But now you see why in the equation we had to do that. Now, we need to deal with this part right here. Remember that n-1, we've lost a degree of freedom because we're using the sample mean to estimate the population mean. And again, that may not mean a whole lot to you now, but hopefully you understand each time we estimate something, we lose a degree of freedom. More on that later. So 1 minus n-1. Very simple. We have 5 dogs. That's n. So 1 divided by n-1 gives me 1/4 or 0.25. So now I can put it all together, right? I can take 0.25 multiplied by 108,520. Take the whole square root of all of that, and I get a sample standard deviation of 165 millimeter. So this is giving me an idea of spread. So one standard deviation would be 165 millimeter. I could look at 2 standard deviations. I could look at 3 standard deviations. Now, keep in mind, gang, that if we were trying to calculate the population standard deviation, we would get a different number because we're dividing by n. So instead of 1/4, it's going to be 1 divided by 5. Obviously, 1 divided by 5 is 0.20, and that gives me 147 millimeters. So slightly different answer. All right, so back to our dogs. Once I have calculated standard deviation, I can see which dogs are within one standard deviation of the population mean. So do you see that I've calculated one standard deviation above, well, 147 above, 147 below, and put in those blue lines. All right. So now I know that the first dog is more than one standard deviation above the mean, right? This is going to help us get a sense of normality. Which observations are normal and which ones are kind of out of the ordinary. So as we've already mentioned, standard deviation is a way to get a standard measure of spread, and it's going to help us get a sense of what is normal and what's not so normal. So in this case, what do I mean by normal or not so normal? Well, which dogs are extra large dogs? Clearly that first dog is an extra large dog. And which dogs are extra small? Clearly the third dog is an extra small dog. You guys get the idea. So as we said, standard deviation is useful because it's a measure of how spread out the observations are. And just to remind ourselves, we use that Greek symbol sigma for population, and we use S when we're talking about a sample. Now, you've also heard the concept of variance, and that's a related concept. So I have standard deviation, which is a measure of spread. Well, variance is a related concept. It's also a measure of spread. There's a simple equation that ties these two together. So variance is simply sigma squared. All right. So all I have to do then is take the population standard deviation and square it. So variance is nothing more than the population standard deviation squared. But if I want to go in the opposite direction, if variance is standard deviation squared, then standard deviation has to be the square root of the variance, right? Because the opposite of square is the square root. So hopefully that makes sense to you. I'm assuming that you're familiar with what we mean by squared terms and what we mean by square roots. So we're going to do just a simple numerical example just to make sure, and I apologize if I'm insulting anyone's intelligence, but I don't want anyone who hasn't looked at math for a while and maybe you're coming back to school to feel like they're being left behind here. So let's just take a second and look one more time. We've got our equation for sample variance, and notice it doesn't have that radical on it. And then we've got our equation for sample standard deviation, and it does have the radical. One is simply the square root of the other. But other than that, they're exactly the same. So variance and standard deviation are very similar measures where one is the square root of the other, or one is the square root of the other. So we square the standard deviation to get the variance, and we take the square root of variance to get the standard deviation. Plain and simple. So let's say I'm starting with a sample variance of 18.62. If I have a sample variance of 18.62, can I calculate the standard deviation? Of course. So how would I do that? I need to take the square root. So the square root of the variance is going to give me the standard deviation. So 18.62, when I take the square root, everyone should have gotten 4.32. All right, easy stuff, gang. Now, let's use standard deviation. There's a couple places where we see some applications, and one of them is Chebyshev's theorem. And Chebyshev's theorem says very simply, for any set of observations, and it doesn't matter if we're talking about the sample or the population, for any set of observations, the proportion of the values that lie within k standard deviations of the mean is at least 1 minus 1 divided by k squared, where k is any value greater than 1. Okay, well, woo, that's a lot, right? So what are we simply saying? Okay, we're saying, look, k can be anything you want it to be. 1 standard deviation, 2 standard deviations. So for any set of observations, the proportion of values that lie within 1 standard deviation or 2 standard deviations or 3 standard deviations, whatever you're interested in, of the mean can be calculated by this equation, 1 minus 1 divided by k squared. So whatever k is that you're interested in, 1 or 2 or 3 standard deviations, we can find the proportion of values that lie within those standard deviations. So still might be confusing. How do we solve that problem? We do a numerical example. All right, so let's say that the employees of your company donate with each paycheck, and they donate a mean of $64.30. Wow, gosh, my brain's not working. $64.30 to the company's charitable programs for disadvantaged youth. And the standard deviation of monthly contributions is $8.65. Okay, so we have a mean contribution of $64.30, and we've calculated from our data on all the employees' contributions, we take that, we calculated the standard deviation, and we found that it's $8.65. Now, we want to know at least what percentage of the contributions lie within 3 standard deviations. Now, when we say lie within 3 standard deviations, we mean plus or minus, right? It could be above or below. So we want to know what percentage of the contributions for all these employees lie within 3 standard deviations. They fall within the range of being 3 standard deviations above or 3 standard deviations below. So then the first thing we need to figure out is, what do we mean by 3 standard deviations? So if I want to think about negative 3 standard deviations, right, 3 standard deviations below, I need to start with my mean. My mean is $64.30 minus 3 times the standard deviation, $8.65 multiplied by 3. So minus 3 standard deviations from the mean is going to be $38.35. But I have to find plus 3 standard deviations. So this would be above the mean. So again, start with the mean, $64.30, and now add 3 standard deviations to that. So $8.65 multiplied by 3 to get added 3 standard deviations gives us $90.25. So I have my 3 standard deviations below the mean, and I have my 3 standard deviations above the mean. So we want to find out what proportion of contributions lie within this range right here. So what proportions of the contributions lie between $38.35 and $90.25? In other words, plus or minus 3 standard deviations of the mean. So we haven't answered the question yet. All we've done so far is dealt with the plus and minus 3 standard deviations of the mean. So now that we have that, so I can use my equation 1 minus 1 divided by k squared. That's going to tell me what proportions lie within k standard deviations of the mean. But remember, we're interested in 3 standard deviations. So k is equal to 3 here. So when I plug in 3, that gives me 1 minus 1/3, where 3 is squared, 1 minus 1/9. So very simple math gives me 0.89. In other words, after I've plugged into that equation, k equals 3, I've learned that 89% of the contributions fall within plus or minus 3 standard deviations. Now, I didn't need to know what plus and minus 3 standard deviations actually was, but I think it makes the problem a little more understandable. So if you go to your boss and say 89% of the contributions fall within plus or minus 3 standard deviations of the mean, he might be like, okay, but it might help to tell him what is plus or minus 3 standard deviations. And that's why we looked at $38.35 to $90.25. Now, I'm not saying that this might be the optimal way to report data on charitable contributions to your boss if that's what he wants. I'm just showing you Chebyshev's theorem. And Chebyshev's theorem helps us determine what proportion of observations or values lie within X number of standard deviations. And in this case, we chose 3. Now, another thing that we can do with standard deviations is look at the empirical rule. And this is very useful. So the empirical rule says for a symmetrical bell-shaped frequency distribution, so we know what symmetrical means, right? Left and right are the same. Bell-shaped, we understand that. We understand what we mean by a frequency distribution. Approximately 68% of the observations will lie within plus and minus 1 standard deviation of the mean. And about 95% of the observations will lie within plus or minus 2 standard deviations of the mean. And practically all observations, 99.7%, will lie within 3 standard deviations of the mean. So, if I look at just 1 standard deviation above and below the mean, I'm going to get 68% of my observations. If I look at 2 standard deviations from the mean, I'm going to find 95% of my observations. And if I look at 3 standard deviations from the mean, again, we're talking about above and below, I'm going to get 99.7% of all of my observations. So that's a lot. Let's take a look at a picture, and I think this will be clearer. So here's our symmetric distribution, and we agree it's symmetric, it's bell-shaped. And what we're saying is that, look, for any symmetric bell-shaped frequency distribution, I can identify 68% of observations by simply looking at 1 standard deviation above and 1 standard deviation below the mean. And I can find 95% of my observations by looking at 2 standard deviations above and 2 standard deviations below the mean. And then finally, if I look at 3 standard deviations above and 3 standard deviations below, I'm going to have almost all of my observations, 99.7% of my observations falling in that range. Now, this can be very useful information because it describes a distribution. And so we will be able to use this type of information a little bit later. So let's tie this into decision making when we're working with data. And let's go back to this survey on job satisfaction. So suppose you survey your departments about job satisfaction. And again, you're asking them to rate on some scale 1 through 100. And let's say the results of your investigation generates the following data. That mean job satisfaction for accounting is 87.2. And for marketing, it's 72.3. And for sales, that division, it's 81. Well, you can certainly make some conclusions here. But as I've warned you about in the past, you need to be very careful what you claim. What we're saying is that the mean level of satisfaction for accounting is higher than it is for marketing and higher than it is for sales. But that's the mean observation. And we can say that the mean level of satisfaction is lowest for marketing. So certainly there's some useful information here. It might make me wonder what's going on in my marketing department where my mean is so much lower. But what I don't know, is this driven by 1 or 2 people that give very extreme results? I don't really know. I don't know anything about spread. So based on just this data, what can we conclude? Well, our conclusions are going to be a little limited, and we do need to be careful. Instead, what if we had data on standard deviations as well? So what new information have we learned if we report standard deviation along with the mean? Well, now this is very interesting, right? Because let's look at our marketing department. They had the lowest mean level of satisfaction, but they also have the lowest standard deviation. In other words, the observations of all the individuals who filled out the survey, well, that spread is a lot tighter. And look at our sales department. Now, the average level of satisfaction is higher for sales, but they also have a much larger standard deviation. So now the story's not quite as clear, and I would need to do a lot more investigating here. So this tells me that the satisfaction level for marketing is lower than the others. I can't say it's statistically lower because I don't have any inferential tools being used at the moment, but that there's maybe more consistency in the evaluations, that people tend to respond more similarly than, for example, in the sales department. In the sales department, there's a higher mean, but there's less consistency, more spread in those observations. So now I've got more to think about if I wanted to do a little investigation. So based on this, as your CEO, are there things that you'd want to think about? Are there things you want to investigate? Is marketing your greatest concern, or now is your sales department a little concerning too? Anyway, you get the idea that mean combined with standard deviation or other measures of dispersion tell a different story, and we definitely need to have a better idea of the big picture by thinking about measures of central tendency, but also measures of dispersion. Now, later, we're going to be able to make even stronger conclusions from our data. Right now, I'm not able to make super strong conclusions. I can talk about means, and I can talk about spread and whether it looks like there's less or more consistency in how people are responding to a survey. But in the inferential section of this class, we're going to be able to ask questions like, are these means statistically different from each other? It might be that two numbers are different, but not so different that there's really any statistical value in terms of the difference. So are these means statistically different from each other? Well, that requires more sophisticated statistics, which we'll get to. Are these standard deviations statistically different from each other? So I see that we've got different standard deviations, but there are tools that will help me learn, really, is there any statistical significance to that difference? But as I said, we have to wait for the inferential statistics portion of this course, which we'll get to. So again, this data we'll be able to do a lot more with when we get to the more sophisticated topics in inferential statistics. So back to this idea of descriptive statistics in general. We've covered many different descriptive statistics, measures of location are mean, median, and mode. We've talked about dispersion, percentiles. Again, remember percentiles is a measure of location, but we use those to get the interquartile range. We talked about standard deviation. We talked about variance. So when describing data, it's best to use a combination of descriptive statistic measures. There's no one measure that tells us everything that we want to know. So for example, you might have a report that looks like this. So this is a study that I did for a school system, and we're just simply here just describing the data set. And notice, before we even get into any sophisticated analysis, and this is a big project with regression analysis and such, I'm reporting the mean and the standard deviation, the min, the max, and the number of observations that I have for each of the variables. So this is just one example of a table of descriptive statistics. This is what I need to do report for my use, but notice I'm not relying on just means or just standard deviation. One without the other doesn't really tell the complete picture. Now, the good news here is that while we've learned to calculate a lot of this by hand, the good news, Excel can do all of this for us, and I'm sure a lot of you have already done these kinds of things. So when we have 10 observations, this is not super difficult, but it sure would be if we had hundreds or thousands of observations. So I want to remind you that you should see the tutorials that are in the module sections on how to use your computer to calculate all of these different kinds of measures, because it's very easy to do so. But as I've indicated previously, you're going to need the Excel data pack. I think it's called the data analytics pack, and there are installation instructions on the modules page. So if you've gotten to this point and you haven't looked through that content, make sure that you have the right package installed so that your Excel program will be able to do these analytical things. And if it's not already installed, I have given you a simple video telling you how to install it. So it's very easy. And this is going to be pretty easy to work with. So the good news is we're going to make Excel do the work. We're certainly not going to calculate this stuff by hand, except for maybe in an occasional quiz type question. All right. But as I said, while Excel will do the work, you still need to understand this. So you're going to be expected to understand how to compute by hand and with Excel. I'm not going to ask you to do these huge, long calculations with hundreds of observations by hand. That would be a complete waste of your time. But you need to understand it well enough that you can answer quiz questions and do some simple calculations by hand, but also with Excel. So guys, as always, thank you for viewing. And if you have any questions about this stuff, please reach out to me. And otherwise, I wish you a great day. I hope class is going really well for you. And I'm happy to help in whatever way I can. So have a great day.